Hello everyone. We are going to continue with the topic tower and tower internals. To start with, we have a little bit of recapitulation. That means what we have talked so far includes the tray towers, and whenever we say tray towers, it means the deck, it means the fittings, which we did not discuss in the last class, but we will do it today, and the vapor dispersers. Now, when we talk about the vapor dispersers, we have found that there are three types. One will be the simple holes, that means the sieve. Then you will have the bubble cap, and you also have the valve type. We also have a look at the pack towers, which will contain two types of packings. One will be the random packings, the other will be the structured packings. What we intend to do today is we intend to cover certain features which are common to both the tray towers and the pack towers. That means, we will look at the different sections of this column and try to see what features are there which are common to both, and possibly we will talk about some special feature which is required in some case. The basic thing that we have to talk about, we will talk about the tray deck first. We will try to understand the construction first. Just if I want to show schematically, a tray deck basically is not a complete circular disc. It is only this part which is present, and this is not there. That means, if I draw schematically, it will come only up to this, and if I take a plan, the plan should look like this. On this, we have the downcomer of the upper tray coming and ending with a gap here. So, what you have in this case is, you have the liquid pouring in, and there has to be a liquid level here. The liquid falling on this tray has to come out of this opening, and it has to flow across the tray, and then finally use the downcomer of this particular tray and go to the tray below. So, this is our tray deck. Now, let us see a few features which are required. Whether we call it a sieve or a bubble or a valve tray, a bubble cap or a valve tray, the basic principle is the same. You will have a pool of liquid, you have droplets, you have bubbles which will be rising through this pool. The mass transfer between the vapor and the liquid will be occurring in the interface of the vapor and the liquid here. So, there has to be some arrangement to ensure that what you have here on the tray deck is a pool of liquid. That means, the liquid level here should go like this, and it should have all such fittings, the sieve or bubble or the valve submerged in it. That means, the vapor disperser should remain submerged. Now, once this has happened, we know that we are going to have the vapor coming from the bottom, the bubbles will go up, and naturally the vapor will be going up this way. Now, I come to the earlier problem which I just stated, that how do I ensure that I have a level of liquid on my tray. The simplest way to do it is to provide here a vertical sheet of metal which will be restricting, and if the liquid has to go from the left to the right, it has to flow over it. So, you have a flow over the wear and you have a throw. Now, let us see, you have the vapor coming in here and you have the liquid which goes like this, and this liquid basically comes from the upper tray which is here. It is also possible, that means I will definitely be having another tray above this. So, if I have a very little amount of level in this particular downcomer, and this depth is called the backup, or this is the downcomer backup, this particular depth. If I have a very little amount of downcomer backup, it is also possible that part of the gas will start short circuiting through this. So, I must also ensure that I have, during my operation of a good cross flow tray, the liquid phase like this and a reasonable amount of backup in my downcomer. Otherwise, what will happen? The vapor will start short circuiting through the downcomer of the upper tray and will be mixing with the vapor of the tray above it. So, you will be losing efficiency in your fractionation. Now, how to ensure the downcomer backup? If you look at this portion, it looks like this. I have my tray deck, my downcomer ends here, I have some amount of downcomer backup here, a liquid level, and the liquid comes like this, goes like this, and it flows in this direction. It is this gap or clearance below the downcomer which provides a resistance, and this is the major component of the resistance which supports this particular liquid column. This liquid column is primarily supported by the resistance offered as the liquid passes through below the downcomer clearance, through the clearance. So, one thing is true, that if I somehow have a very low liquid level or very low liquid flow in my column, the resistance, even with a small downcomer clearance, typically such clearance in industrial columns are never below 4 millimeters. No dimension in industrial column should ever be below 4 millimeters, 3 to 4 millimeters usually. Particularly if it is a clearance, then it will get choked up if you are having any smaller clearance. So, if in such case, if I have to maintain the downcomer backup, I may require another wear here right after this to provide an additional resistance to the liquid flowing out. So, I have now come across two things. One is outlet wear. The second one is some sort of inlet wear. What we do now is we have a look at the other features of how the tray is constructed. The tray, as I have said, is actually only this part. Now, you will have your vapor dispersers quite well located here. The next question perhaps you will have is, how is this tray to be fixed? We always draw the tray as something which looks like this in a schematic. this is my outlet where this is the downcomer of this particular tray, this is the downcomer of the upper tray, and we always say the liquid flows like this over the ware here. Now, quite naturally, such a tray has to be fixed to the wall of the column. That means, I will be fixing it on some fixture which is there, which is permanently fixed with the column. It will be bolted. We will look at the features of those. Quite naturally, if you are bolting it here, you cannot have anything, any vapor dispersers placed in this area. So, this area will be the end wastage area. You will also notice that the actual cross flow path is only from this point to this point on the tray, and it is through this zone only the vapor goes up. So, what you have here is this is going to be your flow path length, and it is the path of flow, and there is this very special thing you must have noticed already, that it does not have the same flow cross section. It is maximum at the center, minimum at the starting point and at the end. We hope to have an uniform flow, but it never happens. So, this is also one such reason why you do not achieve 100% tray efficiency. It is obvious that this portion will not have any perforation. It will have the fixing arrangement with the tray support ring, and naturally, since this is the area which is under the downcomer of the upper tray. So, this is the downcomer seal area. There are downcomer seals which are provided, there are downcomers without the seal also. The seal we will see what exactly it is when we go to the further diagrams. Immediately after it comes out, you have lot of turbulence. Quite possibly, you will not be placing here your vapor dispersers too close. So, quite naturally, what you have after it has come out from this is another zone where you do not put your vapor dispersers. Exactly in the same way, you will not be putting the vapor disperser right before your outlet ware. So, this central area is the area where you have either the sieve holes or the bubble caps placed, or the valves being placed there. Here is what we have in an actual tray. Say, let us say the tray diameter is 2 meters. It is a 2 meter diameter tray. Now, the first question is, we were saying that the 2 meter diameter, how will we fix the tray? So, what will be there is actually something like this. You will have a tower, on which a ring will be fixed. I am not showing this part of the ring, and on the ring the tray deck will be placed. Naturally, the ring is this one, and in this part this is the ring. Now, there is one more thing, the tray has to be fairly rigid. I cannot have any sort of sagging here. In fact, there is a sagging limit. When you check your construction, you ensure that your limit is within that particular sagging limit, and normally you check it with a water level. Now, we have talked about a 2 meter tower, which is very common. Now, that means your tower diameter is 2 meters, and 2 meter is also the diameter of your tray. So, one way is to have the tray and the tower constructed together, but that is impractical. How will you replace the trays in that case? So, what is done? The trays are, particularly in such type of towers, are always in segments. This is a segment, this is a segment, this is a segment, this is a segment, this is a segment. That means, all these are segments, and these pieces are assembled inside the tower. Now, the question comes, how will you place it inside? Your tower shell has been erected. So, quite naturally it has to go through the manholes. Typical manhole size will be anything 20 inches or 24 inches or usually 22 inches. That means the second largest dimension of your tray segment has to be such that it can be passed through the manhole. So, quite naturally by this time you must be appreciating that the dimension of the tray segments have got a very strong relationship with the size of the manhole which is there on the tower shell. Now, once you have put these, they are to be assembled. So, naturally you require a support from the bottom. Usually there will be at least one major beam. This is the major beam. That means it is a diametrical beam which is providing a sufficient support, a good amount of support to the tray on it. You also have minor beams. This is the minor beam, this is the minor beam, this is the minor beam, this is the minor beam. So, you have the minor cross beams which are also attached to the major beam, and they end at where? They end at the tray support ring itself. And what you have boltings all along. The tray support ring is bolted. There are boltings on the minor beam support. There are boltings across the major beam support also. I believe by this time you have got a fair idea how the deck is placed. You will definitely notice that here there is a downcomer and a wear. Here only the wear portion is shown, the downcomer is below this, that is not in view, and that is also bolted. Now, you have a query, you have a very interesting situation here. Suppose I have a downcomer, which has to be placed. How is it? If I look at the tower, its center is here and I require a downcomer to be placed here. I cannot afford to have any leakage across this. So, what is done? You have here a bar welded, which is called a bolting bar. In fact, there are two bolting bars at the two ends of the downcomer, and your downcomer below the deck is bolted here. You have a bolting here. Let us look at a little bit further details beyond this. It is the same diagram that you have here. There is nothing else. It only mentions that below the tray support ring, you usually have an angle to provide extra strength. It may be there in some cases, it may not be there in other cases. So, what features we have so far seen regarding construction? We are aware of the tray support ring, which is a circular ring, not complete circle of course, but it is welded to the tower shell. It is bolted to the deck. The tray deck is fitted on the TSR and the support beams that we have already seen. The beams may be simple beams or it could be trusses even. The trusses are used in case you are having a case in which your construction dimensions are really big. Bolting bars are welded to the tower shell that we have seen. Now, the downcomer apron card is bolted on the bolting bars. So, this ensures the placement of the deck, and on the deck, whether you have the orifice which is the sieve or the bubble caps or the valves, these vapor dispersers are placed or fitted. Now, what we do is we talk about a packed tray. Normally, whenever we talk about a packed tray, we talk about the different shapes of packings that are used. We can just have there are different names. I am more than sure that you have learned about the names of these. There are saddle shapes, bulk saddle is one, interlock saddle is another. You have ball rings, and there are plenty of proprietary packings. What is the purpose of the packing? The purpose of the packing here is primarily to ensure that the specific area in meter square per meter cube of the packed bed that goes up. What is the advantage you have? Ideally, if you have a packed bed, the surface of the packing should be kept wet with the liquid, over which or across which the vapor would flow. There are two types of packings. One way is use all these packings which are all random packings. What we do here is basically we take the tower, we dump it. So, what you dump your material here, your packing material here, and you build up a bed. Here we have an example where there are two types of packing present. This portion is your random packing, but this portion is called structured packing. Let us see what exactly it is. Structured packings basically they have definite shape. Typically, they are sewn together. In fact, they are layers, or rather they are blocks of, these are basically blocks of packing sewn together. This you can see from this diagram itself. So, what you do or what you normally find is these will have a circular cross section and it will be placed here. What are the advantages of this type of packing? They offer you a higher A, number one. The second thing, they offer you a lower pressure drop per depth. So, both way they are advantageous. Now, if you are talking about the packed bed or the tray tower even, there will be other components. You will definitely have a manhole. Here it is a vapor liquid conducting. So, there will be a gas or a vapor inlet and a gas outlet. Naturally, the inlet is from the bottom and the exit is from the top. Here this particular case there are two manholes. You have a liquid from the top and there has to be distributed. In fact, in case of any packed bed, distribution of the liquid is extremely important. If the uniform distribution is not ensured, part of the packing will remain unutilized and possibly your total efficiency of conducting will be falling drastically. What happens is quite often one may require, in case of packed towers, some amount of redistribution as well. This particular tower has got a redistributor. That means, it collects all the liquid which is falling from the upper section. Then what it does is it redistribute. In fact, the construction of this redistributor and the distributor is not much different. Let us look at the various sections of these two towers. The left one obviously is a tray tower. You have trays here, and the right side you have a packed tower. Naturally, you have the packing. If you are talking about the packed tower, the packing requires a support because its weight has to be supported by something strong. So, often you will have a packing. This could be a grill type of structure. It could be a perforated plate as well. It is obvious the opening in the grill or the perforated plate should be such that the packing element should not fall through those. quite often what is done is you have this particular support, on that you have a set of bigger packings, on that you will have your smaller packings. The bigger packings will be ensuring that you have a fair amount of gas and liquid distribution here among the smaller packings, and the smaller packings do not fall off. In fact, what we will always find is not only that there will be a packing support and possibly some sort of bigger packings or larger size packing right above it, you will also ensure, it will also be ensured that your smaller packing pieces at the top do not fly off whenever your velocity is high. So, you usually will be having a bed limiter also. A bed limiter will also be a similar kit or a perforated plate. Remember, all these add to the pressure drop in your column. So, whenever you are designing, you have to ensure that you are always within the total pressure drop, and when you estimate your total pressure drop, you must include all the components through which the vapor has to flow through. Typically, if it is a distillation column, you will have a reflux entry. The same thing is true in case of the tray as well as the bubble column. You are going to have a feed section. You are going to have a feed section in both, and you are also going to have a bottom section as well. In your bottom section, if you are talking about a vapor liquid contacting column for distillation, what you are going to have? You are going to have an entry for your reboiled vapor. You are going to have an takeoff for your bottom product. Where will this bottom product go? Part of it will be vaporized, and it is going to generate the reboiled vapor, which is sent back to the column below the bottommost tray that you can see here, and part of it will be taken off as product. Similarly, in large columns, not always very common in all applications, there may be intermediate refluxes which are called circulating refluxes also. That means, you will have to have an arrangement for taking off some part of the liquid from your column. So, you will require some sort of liquid draw off arrangement. So, what you have here, the liquid draw off arrangement could be for a side stream draw, or it could be for a circulating reflux also. So, we just very quickly have a look that what are the sections of typical columns that we are going to concentrate on. The tower top section, then you have a feed section, the bottom section, the side stream draw off, and a liquid distribution zone where we are dealing with a pack tower. I will just add one more thing here. When the vapor goes off, we do not want liquid droplets to be entrained in it. So, what you usually have is a demister pad above, or rather just below the exit of the overhead vapor, and it is nothing. It is typically around 100 millimeter thick stainless steel wire gauze fixed there, so that the fine droplets of liquid hits it, get stuck, coalesces into bigger drops and fall off, and the vapor which goes off is practically free of liquid droplets. Now, what I say here is, I show you here that the purpose of the practical tower is realization of the number of ideal stages which are estimated to be required for the separation itself. Now, in order to do it, you shall be requiring the temperature, pressure, volume and the liquid flow rates, and also the gas flow rate and the properties in the different sections of the tower. And what you deliver, initially you deliver a preliminary design which consists of material of construction, general arrangement and the gross dimensions. The gross dimensions to start with will be the total height of your tower and its diameter. The final delivery that the designer has to provide is a fabrication drawing which will go to the fabricator, with which he will start fabricating his tower, and then it will come to the field and will get installed. I think with this I will stop here. In the next class what I will do is I will start with the individual sections that I have mentioned in the last slide, and will give you certain dimensions and considerations for arriving at those specific features which are present in those sections. Thank you.